Okay, we're going to do a review for the first unit test on molecules to atoms. And there are going to be several pieces to this to keep the segments short. So let's get started. The first one is on the model of the atom. There were 5 models that we focused on. The first was Dalton's model. That was the solid sphere. The second was Thomson's model. That was commonly called the plum pudding model, but we said in more modern terms we could call it the chocolate chip muffin model. Rutherford was the next model we looked at. Rutherford was the scientist who did the gold foil experiment, and he had the model with a dense positive nucleus. Bohr had the planetary model. And then lastly, the more modern model of the atom, which was the electron cloud. And this sort of told us a probability of where we would find the electrons outside of the nucleus. Okay, so here's a picture of Dalton's model. We've seen this before. This is that solid sphere model. The atoms could not be divided into smaller particles. They were solid, indivisible spheres. Each element had a different atom. So each element was different from each other, and each of the elements bonded in a specific way, set ratios of one element to another, and this explained that predictable outcome of the chemical reactions. We looked at this when we did our molecular structures. When we looked at our little carbon atoms, we had balls that sort of looked like this, that had holes in them. Carbon had 4 holes, oxygen had 2 holes, hydrogen had 1 hole, and we noticed that they could only bond in a certain way in order to form these chemical compounds that we were working with. Thomson's model came next, and this again was called the chocolate chip muffin model or the plum pudding model. Atoms were made up of this positive stuff or goo. We see it here that represents the muffin mix itself. And it had negative charges scattered throughout. You see these electrons sort of scattered throughout that positive goo. The electrons would be represented by the chocolate chips within the muffin batter. Rutherford came next. He had this gold foil experiment. We did a similar experiment by shooting marbles at a wooden block and to determine the shape, and Rutherford shot particles at the atom and looked at how they were deflected in order to determine the structure of the atom. And he found out that atoms were mostly empty space. We can see that here. There's a lot of empty space within our model. It had a dense positive center. We can see that right there in the center. And that there were negative charges within the atom, but they were outside of that positive center. This differs from Thomson's model in that there's a fixed region for that positive center. There it is, and the negative charges are outside. In Thomson's model, the positive charge and negative charges kind of mixed together. Remember that batter with the chunks all throughout it. Bohr had the planetary model. As you look at this model here, we can see it looks like our solar system with the sun in the center and the planets orbiting. This would be like planets with their moons orbiting, but nevertheless, Bohr had this planetary idea of his atom. He focused on the placement of the electrons around that nucleus, and he called them energy levels or orbitals, and they were outside of the nucleus. Each energy level contained a maximum number of electrons. The first energy level could hold a maximum of 2, the second 8, and the third could hold up to 18. Recall that they don't always have that number. That depends on how many electrons are in the atom. For example, hydrogen has 1 proton and a neutral atom has 1 electron, not 2. And lithium had 3 protons and therefore it had 3 electrons, so it would have these 2 filled and 1 more in the second level, but not necessarily all of these. That depended on the atom we had itself. The number of electrons in the outermost energy level determines the interaction between the atoms, and those in the outermost energy level are called valence electrons. So if we look at this model here, the electrons in that third energy level would be considered the valence electrons, although this is really a bad way of looking at it. We're going to talk a little more about some additional facts on the Bohr model that we've discussed. Okay, so one of the other important things was Bohr had said that the electrons have to be kind of in this lowest possible energy level, and that's called their ground state. So if we look here and we have one electron, it's going to be in that first energy level. That's its ground state. We can add energy in a specific amount. So if we take a specific amount of energy, and that's what they mean by photon, remember light is just energy. If we put some energy into this electron, we can actually get it to change energy levels. You see it here going from this first energy level to the second energy level. When we do this, the electron is now in what we call an excited state. Okay, so here it's in its ground state, that's the lowest possible. We add energy, we get it excited, we get it up to the next energy level. It's now in an excited state. They're not stable here. They won't sit in that higher energy level forever. At some point they're going to want to return to the lower energy level where it's more stable, and when they do this, they release energy. That energy that came in, some of that energy is released back out in the form of light. And remember, in our discussions from last semester, light is just a form of energy. The most stable configuration of electrons is when those electrons are in the ground state. So again, if we go back to our example of lithium from the slide before when I was talking, lithium would have 3 electrons in a neutral atom. So there would be 2 in the first energy level and 1 in the second energy level. And when you have 2 in that first energy level and 1 in that second energy level for lithium, that would be considered the ground state. If we excited that second energy level electron up to a higher energy level, that would be an excited state, and it would not be stable. At some point, that electron's going to want to fall back down to the energy level where it would be more stable. You can think of this like stairs. Okay, so here again, if we have we fill that first energy level, we fill that second energy level, and here would be the electron in its ground state. But if it has too much energy, it would be up on this next step up, but it's not going to want to stay there. It's going to want to fill each step before it fills the other. You can think of it like holes. You don't want a hole in the area below you. It just makes it less stable. Here's another picture if it helps. Here we have an electron in its excited state, and it wants to go back down to its ground state, because we would normally have 2 in the first, up to 8 in the second, but this one's not in the second, it's in the third. Well, that leaves space down here in this second energy level where that would be. So this is in its excited state, it's going to go back down to its ground state, and then when it does that, it releases energy. All right, then the last one that we talked very, very briefly about, you read about it, and we had a very brief discussion and showed you some posters in class about it, is not one that we deal a lot with, but this is the modern model of the atom. It's called the electron cloud model. It is the most accurate model, and the electron cloud takes the place sort of that energy level or orbitals, although we use these terms really interchangeably. The cloud is really an area where you have a probability of finding electrons. They're not fixed orbitals as described in the Bohr model. So you notice here, these are examples of the orbitals, of the energy clouds. They're not a fixed spot like that track that Bohr had them on. It's actually a cloud, and in here, in that big cloud, are really 2 electrons racing around so fast you can't necessarily see exactly where they are at any particular time. if you go back to the video on electrons, I'm not sure how many of you actually had a chance to watch that, but it was on the back of one of those independent exercises. They show you an example of why it would look like a solid sphere even though it was individual particles running around. The shape of the clouds are somewhat complicated. As you can see here, there are all kinds of crazy shapes, and we didn't discuss this at length. We aren't going to. There's no need at our level of how we're exploring chemistry this semester. If you take a year-long chemistry class, you will actually talk about this a little more and about how electrons truly are put into those energy levels.